Hello friends, today I will discuss the parallel resonance. Here L is in series and branch is connected in parallel with capacitor which is in series with the RC resistance. In this topic we discuss the definition of the resonance, variation of jet with frequency and resonance frequency, and variation of the voltage under resonance condition. So what is the definition of the resonance? Resonance is nothing but when the applied voltage is in phase with the current flowing through the circuit, then the circuit is said to be in resonance. In the present circuit, RL is in series with L, whereas RC is in series with capacitor C, and these two branches are in parallel and connected to the AC supply whose frequency is variable and applied voltage is V, and the total current supplied by the supply is I. To get the resonance frequency for this circuit, it is easy to apply the admittance and get the resonance frequency. For this branch, the admittance can be written as YLB, means inductor branch, is equal to 1 over ZLB, means 1 divided by impedance of this branch. Similarly, YCB, this is the admittance of this branch, which is equal to the 1 over ZCB, means the impedance of RC and C branch. In this parallel circuit, it can be written total admittance as Y is equal to YLB plus YCB. Substituting this ZLB value and ZCB in this YLB and YCB, then Y can be written as Y is equal to 1 by RL plus J omega L plus 1 by RC minus JXC. Multiplying the first term conjugate of the denominator in the denominator and also multiplying numerator with this conjugate of the denominator. Similarly, in the second term also, by multiplying the numerator with the conjugate of the denominator and also multiplying the denominator with the conjugate of the denominator value. So that is RL minus JXL, that is conjugate of this coming in the numerator. The same thing will be repeated in the denominator also. RL plus JXL, its conjugate is RL minus JXL plus, so here this is RC minus JXC. So multiply this denominator with its conjugate, that is RC plus JXC into RC minus JXC, and same thing put it in the numerator, that is RC plus JXC, which is conjugate of the denominator. And further separate this real part and imaginary part from this equation, then the Y equation becomes RL by RL square plus XL square plus RC divided by RC square plus XC square plus J into XC by RC square plus XC square minus XL by RL square plus XL square. As we know, at resonance condition, the imaginary part of Y, that is admittance, is equal to 0. So making this equal to 0, that is XC divided by RC square plus XC square minus XL divided by RL square plus XL square is equal to 0. And then transferring this to the right, then the equation becomes XC divided by RC square plus XC square is equal to XL divided by RL square plus XL square. And further it can be written as XL divided by XC, that is transferring this to the here and this to here, then XL divided by XC is equal to RL square plus XL square divided by RC square plus XC square. And XL can be written at resonance condition as omega RL. Similarly, capacitive reactance can be written as 1 by omega R into C is equal to RL square plus XL square divided by RC square plus XC square. And further, XL can be replaced with omega R into L, whereas XC can be replaced with 1 by omega RC here also. So then after that, by simplifying, the equation becomes omega R square LC is equal to RL square omega R square L square into omega R square into C square divided by RC square omega R square into C square plus 1. Then further after simplification, that is this here omega R square, here omega R square going to get cancelled, and here 1C going to get cancelled with this C here, and L remains here, and similarly here C will be there. Then the equation will become like this after cross multiplying, that is RC square omega R square C square plus 1 into L is equal to RL square plus omega R square L square into C. And it can be further simplified like this: omega R square into R square RC square C square L minus L square C then is equal to RL square into C minus L. Means this L coming this side and this is multiplied with this. So the equation becomes like this. Then from this omega R square can be further written like this: RL square C minus L divided by RC square C square L minus L square C. And in the denominator, taking LC common, the equation becomes like this: denominator LC into RC square into C minus L, and the numerator is as it is, that is RL square C minus L. And further, omega R can be written as under root of RL square C minus L divided by LC into RC square into C minus L. This is the final resonance frequency equation for this circuit. Suppose if RL value is equal to RC is equal to 0, in that case the omega R becomes 1 by root LC. So which is equal to the resonance frequency of series RLC circuit. Here also it can be observed that frequency versus current. The current is minimum under resonance condition. That is here this is the resonance frequency and the current is minimum, whereas to the left of the resonance frequency current is more. Similarly to the right of the resonance frequency current is more, and whereas the voltage across the circuit is maximum at resonance frequency, that is when current is minimum, voltage across the circuit is maximum. And it also follows the power factor condition also, that is, so when circuit is under resonance current is minimum and the power factor is unity here, whereas to the left of the FR the power factor is lagging, whereas the right of the FR power factor is leading. And here this is the minimum current shown, and whereas this is the maximum voltage Vmax, and whereas this is the half power condition where the voltage becomes Vmax divided by root 2 and the frequency corresponding is F1, F2. And the F2 minus F1 will indicate the bandwidth of the circuit,